Have you ever thought about how a robotic vehicle commonly used in military applications with bomb detonation is controlled? Or how metal cutting and forming machines provide precise motion for milling, lathes, and bending for metal fabrication? Or how an antenna positioning system controls the precision in azimuth and elevation? As you'll learn in this lesson, servo motor applications are most commonly used in closed-loop systems, where precise position control is commonly found in industrial and commercial applications. In this lesson, we will discuss what a servo motor is and how it works. So let's first determine what a servo motor is and examine some unique features of the types of a servo motor and its application. Servo motor basics. Let's begin with the servo motor basics. Servo motors are part of a closed-loop system and are comprised of several parts, namely a control circuit, servo motor, shaft, amplifier, and either an encoder or resolver. A servo motor is a self-contained electrical device that rotates parts of a machine with high efficiency and with great precision. The output shaft of this motor can be moved to a particular angle, position, and velocity that a regular motor does not have. The servo motor utilizes a regular motor and couples it with a sensor for positional feedback. The controller is the most important part of the servo motor, designed and used specifically for this purpose. The servo motor is a closed-loop mechanism that incorporates positional feedback in order to control the rotational or linear speed and position. The motor is controlled with an electric signal, either analog or digital, which determines the amount of movement, which represents the final command position for the shaft. A type of encoder serves as a sensor providing speed and position feedback. This circuitry is built right inside the motor housing, which usually is fitted with a gear system. Types of servo motors are classified into different types based on their application, such as the AC servo motor and DC servo motor. There are three main considerations to evaluate servo motors. First, based on their current type, AC or DC, and secondly, on the type of commutation used, whether the motor uses brushes, and the third type of consideration is the motor's rotating field, the rotor, whether the rotation is synchronous or asynchronous. Let's discuss the first servo consideration. AC or DC consideration is the most basic classification of a motor based on the type of current it will use. Looking at it from a performance standpoint, the primary difference between AC and DC motors is in the inherent ability to control speed. With a DC motor, the speed is directly proportional to the supply voltage with a constant load, and in an AC motor, speed is determined by the frequency of the applied voltage and the number of magnetic poles. While both AC and DC motors are used in servo systems, AC motors will withstand higher current and are more commonly used in servo applications such as with robots, inline manufacturing, and other industrial applications where high repetitions and high precision are required. Brushed or brushless is the next step. A DC servo motor is commutated mechanically with brushes using a commutator or electronically without brushes. Brushed motors are generally less expensive and simpler to operate, while brushless designs are more reliable, have higher efficiency, and are less noisy. A commutator is a rotary electrical switch that periodically reverses the current direction between the rotor and the drive circuit. It consists of a cylinder composed of multiple metal contact segments on the rotor. Two or more electrical contacts, called brushes, made of a soft conductive material, such as carbon, press against the commutator, making a sliding contact with segments of the commutator as it rotates. While the majority of motors used in servo systems are AC brushless designs, brushed permanent magnet DC motors are sometimes employed as servo motors for their simplicity and low cost. The most common type of brushed DC motor used in servo applications is the permanent magnet DC motor. Brushless DC motors replace the physical brushes and commutator with an electronic means of achieving commutation, typically through the use of Hall effect sensors or an encoder. AC motors are generally brushless, although there are some designs, such as the universal motor, which can run on either AC or DC power, that do have brushes and are mechanically commutated. And the final classification to consider is whether the servo motor application will use a synchronous or asynchronous rotating field. While DC motors are generally categorized as brushed or brushless, AC motors are more often differentiated by the speed of their rotating synchronous or asynchronous field. If we recall from the AC-DC consideration that in an AC motor, speed is determined by the frequency of the supply voltage and the number of magnetic poles. This speed is referred to as the synchronous speed. Therefore, in a synchronous motor, the rotor rotates at the same speed as the stator's rotating magnetic field. However, in an asynchronous motor, normally referred to as an induction motor, the rotor rotates at a speed slower than the stator's rotating magnetic field. However, the speed of an asynchronous motor can be varied utilizing several control methods, such as changing the number of poles and changing the frequency, just to name a couple. The working principles of a DC servo motor are the construction of four major components: a DC motor, a position sensing device, a gear assembly, and control circuit. The desired speed of the DC motor is based on the voltage applied. In order to control the motor speed, a potentiometer produces a voltage which is applied as one of the inputs to error amplifier. In some circuits, a control pulse is used to produce DC reference voltage corresponding to desired position or speed of the motor, and it is applied to a pulse width voltage converter. The length of the pulse decides the voltage applied at the error amplifier as a desired voltage to produce the desired speed or position. For digital control, a PLC or other motion controller is used for generating the pulses in terms of duty cycles to produce more accurate control. The feedback signal sensor is normally a potentiometer that produces a voltage corresponding to the absolute angle of the motor shaft through the gear mechanism. Then, the feedback voltage value is applied at the input of error comparator amplifier. The amplifier compares the voltage generated from the current position of the motor, resulting from the potentiometer feedback, and to the desired position of the motor, producing an error either of a positive or negative voltage. This error voltage is applied to the armature of the motor. As the error increases, so does the output voltage applied to the motor armature. As long as error exists, the comparator amplifier amplifies the error voltage and correspondingly powers the armature. The motor rotates until the error becomes zero. If the error is negative, the armature voltage reverses, and hence the armature rotates in the opposite direction. The working principles of an AC servo motor are based on the construction with two distinct types of AC servo motors. They are synchronous and asynchronous, or induction. The synchronous AC servo motor consists of a stator and rotor. The stator consists of a cylindrical frame and stator core. The armature coil wound around the stator core, and the coil is connected to a lead wire through which current is provided to the motor. The rotor consists of a permanent magnet, and this differs with the asynchronous induction type rotor in that the current in the rotor is induced by electromagnetism, and therefore these types are called brushless servo motors. When the stator field is excited with voltage, the rotor follows the rotating magnetic field of the stator at the same speed, or synchronized with the excited field of the stator. And this is where the synchronous type is derived. With this permanent magnet rotor, no rotor current is required. So when the stator field de-energizes and stops, the rotor also stops. These motors have higher efficiency due to the absence of rotor current. When the position of rotor with respect to stator is required, an encoder is placed on the rotor and provides feedback to the servo motor controller. The asynchronous or induction AC servo motor stator consists of stator core, armature winding, and lead wire, and the rotor consists of shaft and the rotor core winding. Most induction motors contain a rotational element, the rotor or squirrel cage. Only the stator winding is fed with an AC supply. Alternating flux field is produced around the stator winding with the AC supply. This alternating flux field revolves with synchronous speed. The revolving flux is called a rotating magnetic field, or RMF. The relative speed between stator rotating magnetic field and rotor conductors causes an induced electromagnetic force in the rotor conductors according to Faraday's law of electromagnetic induction. This is the same action that occurs in transformers. Now, the induced current in rotor will also produce an alternating flux field around itself. This rotor flux lags behind the stator flux. The rotor velocity is related between the rotating stator flux field and the rotor rotates in the same direction as that of the stator flux. The rotor does not succeed in catching up to the stator flux speed, or not synchronized, hence where the type asynchronous is derived. Servo motor applications are applied in many industrial and commercial systems and products, such as with robotics, where a servo motor is used at every joint of a robot to perform its precise angle of movement. The camera autofocus uses a servo motor built into the camera that corrects precisely the position of lens to sharpen the out-of-focus images. And with antenna positioning systems, where servo motors are used for both the positioning of azimuth and elevation axis of antennas and telescopes, such as those used by the National Radio Astronomy Observatory. This concludes the video, What is a servo motor and how it works. I hope you've learned what's required to move forward in creating your own motion control project.